Yes. So it says we have to choose the correct statements. You can have a look at the options, and one by one we can discard the options. So the first option says every subfield of the field C contains Q. So yes, what's your take? It's true or not?
It is true.
Good. Yeah. Well, what's the reason? The statement is true. I agree. So a hint is if it is a subfield, then definitely it will contains 1. So can you say something now? If it contains 1, why it will contains then Q? Yeah, so let me just try to say something more. So let K be a subfield of C, right? Now, as 1 belongs to K, therefore, you take 1 plus 1 plus 1 any n number of times, because it has to be a subgroup under addition. Say this is for n times. This also belongs to K, right? And this is for all n belongs to n. Yes, so this implies that your yes, Hemlata, you want to say something? So this simply implies that n is inside K. Now, also for all n in n, minus of n and in K I can put, because now in our K n is inside K. Minus of n should also be inside K, because again K plus is a group in itself. So it has to be closed under taking additive inverse. This implies that all negative of all natural numbers is also there. So this implies minus of n also belongs to K for all n belongs to n. And of course, 0 is always there due to the same reason that K plus is a group, which implies that the set of all integers is inside your K, right? Now for any say x belongs to z minus 0, X inverse has to be inside K. And this is because K minus 0 under multiplication is a group. Because we are now taking the subfields. Subfields forms a group under addition, and the non-zero elements forms a group under multiplication. So this has to be true. But you have all integers inside K already. So this implies 1 upon n also belongs to K for all n belongs to z minus 0. Right? As I'm already using X inverse, so let me just use X here. So 1 upon X. And what is your rational number? Like so for any P by Q with inside the rationals P and 1 by Q is inside K, right? This implies P by Q is also inside K, and thus your entire set of rationals is inside K. Okay. So I hope this is clear. This is very simple argument. We are just choosing the properties of field, nothing else. In fact, not only for C, if you have a field of characteristic 0, so in fact, you can note that each field of characteristic equal to 0 has the property that each of its subfields contains a subfield, again a subfield, which is isomorphic to Q. What I mean to say by that, this means if say characteristic of f is equal to 0 and say k is a subfield of k is a subfield of f, then there exists some L inside K such that L is isomorphic to Q. So Q is sitting inside K for all subfields. And this is also easy to see, nothing serious happening here. So it's all you need to see is from Q to K, you can simply define the map 1 going to identity, multiplicative identity of 1 of k I am writing. So what I mean by 1 of k, this is multiplicative identity of k. Let's say this map is 5. So if one is mapping to 1 of k, then n, this will implies that simply n will be mapped to uh, 1k plus dot 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 1 of k n many times, and this is also inside k. Similarly, minus of n you can map to minus 1 of k, minus 1 of k, minus dot 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 minus 1 of k, right? And so you have the set of integers inside this, and so on. You can get that any p by q you will get inside it to this depending on whether like p is positive or not. So it will be n times 1 of k or n times minus 1 of k you have, and then for the q it is just the inverse of q. So q already has an image there, so q inverse will also have an image there. So that's like this dot q of inverse. So in this way you can map it there. So q is sitting inside it. So I'm just writing here p of q inverse. Okay, so q sits inside any field in general. Okay. Okay, so first option is correct. What about the second one? The degree of cube root of n over q is 3 for every positive integer n.
For 1, 8, 27, etc.
Yeah, so if n is already a cube root, then it won't happen, because then cube root of n will be inside q. But if n is not a cube root, then that's going to happen, right? So that is what. First of all, you can see that this is true. For second, if n is a cube in q, then cube root of n belongs to q, and then the degree of cube root of n over q is 1, which is not equal to 3. So that is certainly false. Yeah, good, Muthu. So what about the third option? Let me go back to the options again. The degree of root 2 plus root 3 over q is 2.
The degree of root 2 plus root 3 over q is 4.
4, not 2. Yes. So that has already been discussed in the class, but in fact, without proving that its degree is 4, you can still argue that its degree is not going to be 2. So how we can do that? So let's take this K to be the field containing smallest field containing Q and root 3. So the dimension of this field will give you the degree, right? But uh, root 2 plus root 3 is there. So root 1 upon root 2 plus root 3 should also be there because it's a field. This implies you just take the rationalization of this quantity. So it will become, this will be inside K, but this is what? This is root 2 minus root 3, and you have 2 minus 3, which is 1. So minus 1, so you have root 3 root by root 2 is also inside K. So you have root 2 plus root 3, and you also have root 3 minus root 2. That will implies that root 2 plus root 3, this plus root 3 minus root 2. This is addition, and 2 is already there, so you can of course divide by 2. This should also be there inside K. But what it is? This implies root 3 belongs to K. Okay. So now consider this tower. So root 3 is there and Q is already there. So this implies that this field Q root 3 is inside K, right? Because Q is already there inside K, is the smallest field containing Q and root 2 plus root 3. And if root 3 is already there, also there, then Q root 3 has to be there because it is the smallest field containing Q and root 3. So now if you consider this tower, so Q root 2 plus root 3, it contains Q root 3, and Q root 3 of course contains Q. Now the degree of this, it has degree 2 because root 3 has the polynomial. Root 3 satisfies the polynomial. Satisfies the irreducible polynomial. X square minus 3 over Q. It's a degree 2 polynomial and it's irreducible, so its degree has to be 2. So it has degree 2, right? So if so what we have the degree, and we also know the multiplicative property of the degrees, right? So Q root 2 plus root 2 is degree over Q is Q root 2 plus root 3's degree over Q root 3 times q root 3 degree over q, right? Now this may be something, say alpha, okay, and this is say, 2, that we know. Instead of alpha, let me just write it again because it will create rotational confusion. So this, for the moment, we don't know, let's say, but this has degree 2, right? So if q root 2 plus root 3, this has degree 2, then this implies that this degree would also be 2. Oh, sorry, 1, right? Because if you have 2 here, then 2 and 2 will get cancelled, so its degree has to be 1. You agree? So the degree of this over q root 3, this has to be 1, and but this will imply that q root 2 plus root 3 is same as q root 3, and this will give us a contradiction. Why? This is a contradiction since
You can use this multiplicative result provided q of root 2 plus root 3 is a finite extension of q.
q of root 2 plus root 3,
Should be a finite extension of q.
no, this is true even for infinite extensions. If one of them is an infinite extension, then this will become an infinite extension. So we need not
Yeah,
to that any one of them is an
if,
infinite extension.
if the largest one is finite dimensional over the smallest one,
That will force that the lower ones are also finite.
yes.
Yeah.
But here we have not mentioned that the highest one is a finite extension of the lowest one.
No problem. If it is an infinite extension, then one of them has to be an infinite extension.
It's okay.
Right?
But anyway, that result is, we have to mention that result.
So multiplicative thing will follow in any setup. Finite, infinite, that's not an issue. Anyway, we will use these things to prove, to see, in fact, the degree is 4 here. But without using that, just by multiplicative thing, we can say that its degree is not at least, its degree is not 2. Okay. So why this is a contradiction? Because we have already seen that, so root 2, root 3 is already there inside this q root 2 plus root 3. And root 3 is also there inside this that we have seen. And this will implies that root 2, which is nothing but the difference of these two, this is also inside root 2 plus root 3. But you can easily see that root 2 won't be there inside q root 3. And this also has a very naive explanation. So let a and b are inside. So any element of q root 3 is nothing but of the form a plus b root 3, right? Because it has degree 2. So any element is actually of the form this a1 plus a2 root 3 plus a3 root 3 square, and so on, an root 3 n. But after squaring, it is becoming a rational. So this and this you can add, and here whatever the cube root, the cube part, it will become a4, 3 and root 3. So this part and this part you can add. So eventually you will be ending up with a plus b root 3. So any element is of the form a plus b root 3 inside q root 3. So yes, so let a and b are inside q such that root 2 is of the form a plus b root 3. Then this will implies I should do taking a square, just squaring both sides, square a plus b root 3 square. I think it is not a problem. Somehow maybe I can keep a one side and then yeah, it will work. So root 2 square and then a plus b root 3 square I will take. This will implies 2 is a square plus 3b square plus 2b root 3. Now this will implies that 2b root 3 is nothing but a square plus 3b square minus 2. So what your root 3 is? Root 3 is nothing but a square plus 3b square minus 2 by 2b. But this is a rational number. So b definitely we cannot choose to be 0 because b is, if b is 0 then definitely root 2 is a, which is a rational number. It's a contradiction in the beginning. So root b has to be non-zero. That's why this is okay. You have something non-zero in the denominator. So this is inside q, which is a contradiction. So that's why root 2 should not be there inside q root 3, and this is a contradiction. So this implies that q root 2 plus root 3 is not same as q root 3, and thus the degree of root 2 plus root 3 over q is strictly greater than 2. Okay, I hope it's clear. So what we did, we see first that root 3 is inside uh, root 2 plus root q root 2 plus root 3. So if root 3 is there, q is already there, then q root 3, this entire field is a subfield of this. So we have this tower of fields, and then we can just use the multiplicative property of the tower of fields. So q root 2 plus root 3 is degree of, yes, you want to say something? Okay, so q root 2 plus root 3 over q has the degree just the product of q root 2 plus root 3 and q root 3 and then q root 3 over q. So its degree we know that its degree is 2. Here we just saw. So now if this degree is 2, then this has to be 1, and which implies that these two fields are actually same, but we are getting a contradiction in that. So this degree cannot be 1. Thus there is something more than 1 here. So it's multiplied with 2 will give you something more than 2. So this degree cannot be 2, right? So that's why option C is false. Okay. Now, second thing is the degree of root 2 plus root 3 over q root 2 is 2. So
It is
this
true.
this is true. So how to show that? First of all, note that root 2 plus root 3 is inside q root 2 plus root 3, and we show that root 3 is inside this also. So this implies that root 2 is also inside this, because you can just take the difference, which implies that this entire field is inside this. There is no issue in that. Now, root 3 satisfies a polynomial of degree 2 over q. Maybe you can just use that, or if you can get a polynomial in q root 2 which satisfies this, then that is also fine. But in class, we have seen, so let us first consider the tower of fields. Consider the following tower of fields. What tower of fields I want to look at? So we will just look at this tower of fields, q root 2 plus root 3. So we have seen that it contains q root 2, so it's an extension of it, and q root 2 definitely contains q. Now, it has degree 2, right? Since root 2 satisfies the reducible polynomial x square minus 2 over q. It has degree 2. Now we will see what can be the degree of this extension. Okay, so this we don't know. So once we know that, then we can use it to know this also. So let's say this is something alpha. Alpha say. So then by the multiplicative identity, what can be the degree of this? So you have alpha here and you have 2 here, and 2 times this is going to be alpha. So this is nothing but this is it has degree alpha by 2, right? Because this and this degree after multiplication should give you alpha. So what can you say about this degree? So first, let us try to find a polynomial which satisfies root 2 plus root 3. So let us first find a polynomial fx inside q of x that satisfies root 2 plus root 3. Okay. For that, let x is root 2 plus root 3. So you just need to uh, do computation in such a way such that these uh, coefficients become rationals. So now here the coefficients are not uh, rationals. So what can you do? Take root 2 here, x minus root 2, root 3 here, square it. Squaring both sides. So this will become x square plus 2 minus 2 root 2 is equal to 3, which will give you x square. So take the root part to the other end so that after squaring it will removed. So x square minus 1 is equal to 2 root 2. Square it again. This will give x square minus 1 whole square is 8. Right? And this is nothing but x square plus 1 minus 2x square is equal to 8, which will give you x square minus 2x square minus 7 is equal to 0. Oh, sorry, I'm making some silly mistakes here. So this is x4, this is x4, right? Because after squaring you will get this. I hope the calculations are okay. This will be x square plus 2 minus 2 root 2, 3, 1, this will be minus 1, 2 root 2. Square them again, so it will be x4 plus 1 minus 2x square. This will be 8, and then x4 minus 2x square minus 7 is equal to 0. So this satisfies. So this process says that this polynomial x4 minus 2x square minus 7 has root 2 plus root 3 as a root, because we started from here. So after squaring, and this equation is still satisfying, so you can check that this will surely has root 2 plus as a root this irrational number root 2 plus root 3. So what does this imply? This implies that the degree of q to root 2 plus root 3 over q, and this is a polynomial in rationals, right? So degree of q root 2 plus root 3 over q is less than equal to 4, because this might be irreducible, might not be irreducible, so we don't know, but there is a polynomial so which satisfies this. So the minimal polynomial of it, or the polynomial which is irreducible for this root 2 plus root 3, that polynomial will divide this polynomial. Okay, so its degree has to be less than equal to 4. But using multiplicative identity, you note that root 2 plus root 3 over q, this is same as q root 2 plus root 3 root 2. Oh, sorry. What am I doing? This over q root 2, and then you have q root 2 over q. So this is already, this thing is already 2. Okay. And one thing that you can check is this cannot be equal to 1, since uh, root 3 won't be there inside just q root 2, using the same technique that we showed that root 2 is not there inside q root 3. Similarly, you can see that root 3 is also not there inside q root 2. Okay, so this is not equal to 1, so this is definitely greater than 1. So what, from all these things, what can you get? So this implies that its degree is between, cannot be 2 because it's not equal to 1. This degree is not equal to 1, and this is already 2. So this degree has to be strictly greater than 2. So this is greater than 2, less than equal to 4. And also, since this you have 2 as a divisor of this degree, so 2 must also divide, 2 divides this degree. So the only possibility you have is this degree has to be 4, right? This implies the degree of root 2 plus root 3 over q is 4. And once it is 4, this implies that the degree of root 2 plus root 3 over q root 2 is 2. Because here you have 4 and here you have 2. You just divide it, you will get 2. So the so we did both things in one way. In that we also proved that this degree is 4, and then uh, as an immediate consequence of it, we get this, the degree of this extension is of 2. So this is what was asked in the question. So the statement is true. Okay, all good till now. That's what we were supposed to see, that the degree of root 2 plus root 3 over q root 2 is 2. Okay then. So if it is fine, let me just paste the second question. Till then, if you have any doubt, then you can ask. Okay, so it says if alpha is a let alpha be a complex number. Suppose that the degree of alpha over the field of rational numbers is m, and the degree of alpha square over the field of rational numbers is n. Then one has to choose all correct statements. So first of all, just realize that which is a smaller field, q of alpha or q of alpha square. So one field you have q of alpha, other you have q of alpha square. So which is contained in which?
Q of alpha squared is contained in Q of alpha.
Yes, good. So this containment is there, and this is obvious since you have q is inside q of alpha, and alpha dot alpha, which is alpha square, is also inside q of alpha, and q of alpha square is the smallest field containing q and alpha square, so it has to be inside that. So you have this tower. So we again have the tower. Yes. So we have following tower of fields. Q alpha is in the at the topmost level. It contains q of alpha square, and it also contains q. So the degree of q alpha over q is m. So this is m. This is n. So what first condition says, n always divides m. So there is nothing to worry about it. This will definitely implies n divides m by the multiplicative identity of field extensions. Multiplicative identity of field extensions. Okay, so first one is true. What about the second one? N is less than equal to m. That is also like obvious.
When n divides m, n is less than or equal.
Yeah, yes. So that's an obvious thing. N is less than equal to m. This is also true. Third, m is less than equal to n. So this is not necessarily be true. We can definitely consider the above tower of fields that we have, q root 2 plus root 3. This is an extension of q root 2, which is an extension of q. So this has 4 degree and it has 2. So definitely 2 is not greater than equal to 4. So this is false. Okay. Now, if m is a prime number, then m equal to n. So this is also like, if m is a prime number, then m has to be equal to n. What was m? M was the degree of. This seems okay, I think. Or there is some typo here. Because alpha be a complex number, suppose that the degree of alpha over the field of rational numbers is m, and the degree of alpha square over the field of, yeah, this will contradict only if n equal to m, n equal to 1. So for now, consider this tower of fields. You have q root 2. You pick any rational number. This is just q of say 2, and you have q. So this is nothing but q. So n is going to be 1. This is going to be 2, which is of course a prime number. but you can see clearly that n is not equal to m. So the statement is false. Okay. If it would have given you one additional condition that n greater than 1, then of course in that case, if m is a prime number and you have n greater than 1, then it has to be just m. Then n and m are same, because n is going to be a divisor of m, so it's either it's going to be 1 or it's going to be m if m is a prime number. So
Please
yeah.
show me
Yes.
the tower diagram for third one. Third one. Q root 2. There you have alpha squared is not
Oh,
taken care of.
oh. Yes. Thank you. So there is definitely an issue here. So alpha square is not take. So same thing I think we can do. Same tower as we consider in the fourth part that we can consider. Yeah, thank you, Muthu. So this is going to be q root 2, and this we can take to be q2. This is 1, this is 2, and then 1 is not greater than 2. Yeah, thank you very much. Okay. Now I think it's fine. So let me paste the question. Okay, so here it is. It says, let's see, is the field of complex numbers and Q is the field of rational numbers. I is just the square root of -1, root 2 is the square root of 5. K is this field which contain the smallest field containing Q, I, and root 5. Then we have to choose these options, choose the correct options. First one is every field homomorphism from K to C. For every field homomorphism from K to C, we must have sigma of K contained in K. Yeah. So let us see the first part. Any guesses? What do you think? Is it true or false?
Guess is true.
Because the answer is true, right? uh, it just uses simple trick, like where Q is going to be mapped to Q, then what are the choices for I and root 5? So let sigma from K, which is nothing but Q I root 5, to C be a field homomorphism. then sigma of this entire rationals must be equal to, or let me just write it more precisely, then sigma of alpha is equal to alpha for all alpha belongs to Q, so it has to fix the base field. Now, what can you say about root 2 and I and root 5? Also, since I satisfies so there was a theorem discussed in class which says that also via result, which is also easy to see, discussed in the lectures. We know that sigma of I must satisfy the irreducible polynomial of I over Q. What does this mean? This implies sigma of I is a root of, what is the irreducible polynomial that I satisfies? X square plus 1, right? So this implies sigma of I is either I or minus I for any field of homomorphism, right? Finally, root 5 can be mapped to an can only be mapped to a solution of its irreducible polynomial. So sigma of root 5 is the root of x square plus 5 or x square minus root 5 should write. This is x square minus 5. Now this implies that sigma of root 5 is equal to root 5 or minus of root 5. It can be mapped to I. So sigma I can be mapped to I or minus I. Root 5 can be mapped to root 5 or minus root 5. So where does this sigma map K? Right? So sigma maps Q to Q. Okay, first thing, sigma can map I to I or minus I, and sigma can map root 5 to root 5 or minus of root 5. And this will give us the definition of entire homomorphism, because any element of Q I root 5, you can get it where it maps just by knowing these three things. Okay. So because it will be just a polynomial, any element of Q I root 5 is just a polynomial in I and root 5. So if you know where I is mapping, where root 5 is mapping, and where Q is rationals are mapping, so you will know that where any arbitrary element is mapping. But see, these I or minus, this is definitely inside K. I or minus I is already inside K because I is there. Root 5 and minus 5, this is also inside K. So this will implies that sigma of entire K is inside K. Agree? Thus, this statement is true. Okay. So
You can take sigma of -1 equal to -1.
sigma of -1.
-1 equal to -1.
Yes.
That is sigma I squared equal to -1.
This will imply sigma I square is -1. Which
Which
implies
is sigma I whole squared equal to -1.
Yes.
So sigma I is plus or minus.
This implies that sigma I satisfies x square plus 1, right?
It's okay.
Okay. So this is precisely how the result was proved. This result that I'm saying. So if say alpha is any number, alpha is any element, you want to show that sigma I also satisfies, sigma of alpha also satisfies the same polynomial. So that polynomial is nothing but fx is a naught plus say a1x dot 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 an xn. You uh, apply sigma over this entire polynomial. This will become sigma of a naught because it's a homomorphism, sigma of a1, sigma of x dot 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 sigma of an, sigma of xn, x raised to n. But now since the field homomorphism has the property that it will fix your q, so this will be nothing but a naught plus a1x sigma of x plus a2 sigma of x square dot 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 an sigma of x raised to n. So if a1 plus a1 alpha plus so on to an alpha n was 0, then it will imply that a naught plus a1 sigma of alpha dot 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 this will also be 0, because the right hand side is nothing but sigma of 0, which is 0. So if alpha satisfies the polynomial, then sigma of alpha will also satisfy the polynomial. So this is what precisely the proof of the result I was talking about. Okay. I hope this is clear. To delete this, go. Oh, it's not happening. Need to do this. Till then, maybe you can think of the second question, the second part. Okay. So it says any field homomorphism from K to K such that sigma is equal to I must be an identity homomorphism. So I have already said everything about it. You just need to complete the argument. So if a field homomorphism is fixing I, whether it will fix every element of K.
So you can have a homomorphism sigma of I is I But sigma of root 5 is minus root 5.
Yes, precisely. So this statement is false. So second is false, since we have a field homomorphism sigma from K to K such that sigma of I is equal to I and sigma of root 5 is equal to minus of root 5. Yes. So, similarly, the next part is also false, right? Next part says if sigma is a field homomorphism such that root 5 is mapped to root 5, then sigma must be an identity of homomorphism. So you just twist it. What I mean by twist is just consider the homomorphism. So since we have a field homomorphism,
D is true. Fourth one is true.
okay, so let me just see the option fourth. Root 5 is root 5 and sigma of I is not equal to minus of I. Oh, sorry. Equal to minus of I. Oh, this is third one. Yes, so what's the fourth option? It says there are exactly 4 field homomorphism from sigma K to K. Yes, because there are 2 choices for root 5, there are 2 choices for identity, and each of the choices are independent. Thus, there are 4. Good. So this is true. Since if sigma from K to K is a field homomorphism, then first of all sigma of alpha is equal to alpha for all alpha belongs to Q, and sigma of I is plus minus I, and sigma of root 5 is plus minus root 5. There are 2 choices here, 2 choices here, and these choices are independent of each other. One has nothing to do with the other one. This implies there are 4 field homomorphisms. Okay, good. So with that, I think we are done. There are 4 options, right? Yes. So if that is fine, then we can move to the next part, next question. Yeah. So this question might look a bit longer or a bit tricky, but it's also easy, not difficult at all. So it says let M and AB denote the arbitrary positive integers. This is nth root of A and this is mth root of B. The notations are like that. And if alpha is the sum of these two and degree of alpha, this denotes the degree of alpha over the field of rational numbers, then which of the following statements are true? So if alpha not equal to M, then degree of alpha is equal to Mn always. So what you want to say for the first? Any idea? Yes, Muthu, what do you think? What option you submitted?
It is false.
This is false. Good.
You have to
Then give
look
me
for a counter example.
you are looking for a counter example. So the obvious one is to trivialize the situation. What you can do, you can just try first put A equal to B and uh, so that and try to be smart and put your values such that this alpha lies in one of the extension. So for that, take M to be which one which you want to M dividing N. Okay, M such that M divides N. Now what will happen? So alpha is what? Then alpha is A root of N, which is nothing but this and plus A root of M, right? Because B is now over M. So and N divides M. This implies that N is nothing but some M times alpha, or alpha we can't take. So let's say M is nothing but some M times K for some K belongs to N. So this is nth root of A. So this is mth root of A. So you can you write it like that? This is nothing but you take first mth root of A and then take the kth root of it. Is this okay? Because see, this is what? This is nothing but you can take it as A1 upon N, right? In other notation. And A1 upon N is nothing but A mk, which is A1 upon M dot 1 upon K. So you are just taking 1 upon kth power of 1 upon A, 1 upon M. Fine. Okay. Now see, alpha, this belongs to, this is Q, or everything's happening over Q, or okay. So for this, like, we can also, for the sake of simplicity, we can take F to be Q, right? Just for the sake of simplicity, although it's not going to play much role, but let it be like this. So this is going to lie inside Q, A upon N, right? Because this is nothing but A, Q N upon N. And what is this? This is nothing but A N times K, right? Because after taking kth power, this kth root will be removed, right? And you just have mth root of A. So this will also be lie inside this. So their sum will also lie inside this. This implies that alpha is inside qth, nth root, q adjoined with nth root of A, and this will implies that the degree of alpha over q is less than equal to n, right? Because it definitely satisfies this number definitely satisfies the polynomial xn minus a, right? Why I'm saying so? This is because this is because this number satisfies xn minus a over q, right? So the degree of this number over q has to be less than n, and if something is in this, so you can consider the tower and then see that the degree of that alpha has to be less than equal to n. Okay, this implies that q of alpha over q, this degree has to be less than equal to it. So definitely it cannot be mn. Okay. This is a specific case where you consider a equal to b, right? And you get that degree of this is less than equal to n. You can give values to them, can take a equal to b, and for simplicity you can just take this, take a, b, m, all three to be 2 and n to be 4. Then you can see that the degree can be at most 4, but mn is equal to 8, right? So this is not going to be mn in this case. Similarly, you can, this is just a particular choice of integers, but this is what the main idea that you have to use in fact in this argument also. Okay, is the idea clear? or you want me to repeat it once again?
It is okay.
Okay, good. So what about the second option? Degree of alpha is less than equal to Mn always holds.
I think we can find a polynomial over Q satisfied by alpha of degree Mn.
Of degree?
Mn.
Mm, yeah, that is okay. But
So
the-
therefore, degree of alpha must be less than or equal to Mn.
no, it may be greater. You find an polynomial satisfying which satisfies the like degree Mn, but you may find something more. Na? You can find an example where there is just a polynomial of degree Mn plus 1 for some different alpha. This statement says that for any alpha, you will get a polynomial of degree at max Mn, which is satisfied by alpha. If you want to argue it in terms of polynomials. So for a particular choice of alpha, if it that is being hold, then it won't make it true for all alpha, right?
So for every a comma b, if it satisfies,
Yeah, for every a comma b and for every mn. What you are saying that
okay,
will make the statement C true.
for every a comma b and for fixed values of Mn.
Yes, the degree of alpha has to be less than equal to mn. So the hint is this statement is also true, and we will use our best friend in this lecture, that is the tower of fields, to show that. But what tower of fields you think will make uh, the job done?
So the product should be one is M, the other one is N. So product is going to be Mn.
Yeah. Yes. So we have to consider such a field, tower of fields. You are right. So, so here this statement was false, right? Now let us consider the second part. So your alpha is, I have to see it again. I forget. So this is nth root of A and mth root of B. This is nothing but nth root of A and mth root of B, right? And this alpha belongs to, this is inside Q or any arbitrary field. A field of rational numbers, it's saying. Na? This is already inside Q, no need to worry. So this belongs to Q of nth root of A comma mth root of B. You agree? Because this field contains these two, and so their sum will also be there. So alpha is there inside it. Now consider the tower of fields. Here you have Q nth root of A, nth mth root of B. It's your choice whether you want to take here n q nth root of A or mth root of A. There is no issue there. You can choose it nth root of A or mth root of A. One of them you can choose. So its degree, it has degree. It has degree
Less
n.
than or equal to. Less than or equal to. Yeah.
Yeah. So, sorry. Less than equal to n. Okay. Since this satisfies the polynomial xn minus a over q. And here, see, nth root of a is already there, q is already there. So we just need to see what polynomial mth root of b satisfies. So this has degree less than equal to m, since mth root of b satisfies the same polynomial kind of polynomial one has to put there, xm minus b over q, but you can also say this over this because it's a larger field, so q is already there. So the degree of this entire extension is nothing but m times n. This implies q nth root of a mth root of b. It has degree oh no. Uh, can you see anything?
The board is not visible.
Yeah, it just crashed. So let me open it again. I hope the file is saved. Otherwise, I have to rewrite it again. It's opening. Luckily, the file is there. Let me just share that in. Yes. So where were we? Yes. So degree of this field over Q is less than equal to mn. And since alpha belongs to this field, so you can just use the multiplicative identity again and consider the tower Q alpha in this field to argue that the degree of Q of alpha over Q must also be less than equal to Mn, because you can just consider this Q, it has extension Q of alpha, and then you have the extension Q of nth root of A nth root of A mth root of B. So this tower will give you that the degree of Q over alpha over Q is also less than Mn. So yeah, so this makes the statement true, right? So we are not choosing a particular alpha; it is for all, right? Okay. I hope that is fine. Let us move to the third part. Which says there exist positive integers m and ab such that degree of alpha equal to m. Now you have to find such integers for which the upper bound is actually achieved. So this upper bound is strict upper bound, means you cannot uh, get a smaller upper bound for all alpha.
We have already proved root 2 plus root 3 is of degree 4.
Yes. So here we can take A to be 2, B to be 3, and an M to be 2, right? So alpha will become root 2 plus root 3, right? So this is true since for A equal to 2, B equal to 3, N is equal to 2, we have alpha to be root 2 plus root 3, and the degree of Q root 2 plus root 3 over Q is nothing but 4, which is equal to 7. Okay. So it's good to solve such an example in the beginning that it will help in all the cases. So this is a very good example, the root 2 plus root 3. Yes. So now let's see the fourth one. Can I this positive integer m and ab such that degree of alpha is greater than mn? Yes, Muthu, what's your take on that?
D is false.
Yes, this is false because second one is true, right?
Yes, less than or equal to Mn.
Yes.
So cannot
This
be
is
greater
false.
than.
Yes, since second is true. Okay, so with that we are done with. This is question number 4 or what? Question number 4. Okay. So question number 5. Let's see that. Oh, 5 is your favorite question, which you were asking last time, last to last time. there is one more option. Yes. So it says let PQ be distinct prime numbers, and uh, let's say I will say uh, use the notation CP. Okay, whatever this means, the symbol I will, or maybe JIP we will say. So JIP or JIQ denote any primitive pth and qth root of unity respectively. Then Q denote the field of rational numbers. We have to choose the correct statements. So if P is less than equal to Q, then xi P belongs to Q of uh, xi Q. What do you think?
Because there is a result that psi p is not belonging to Q of psi 5. Psi 5 is not a member of Q of psi 7.
Yes, that is okay.
So that is, there are prime numbers PQ such that 5 is less than or equal to 7, but that zeta of 5 is not a member of zeta Q of zeta 7.
Yes. So for that, let us first prove something, maybe, and that is itself a very good statement. And you can see that statement alone in many exams. And in fact, in one of the interview that I faced, the interviewer asked me that question. So something related to that only. So xi has degree p minus 1 over q. Okay, so that is claim 1. So how to show that? For that, first of all, observe that xi satisfies xp minus 1 over q, right? And p is the smallest number such that uh, xi satisfies or maybe I should write it in some what different uh, actually that is also correct. Satisfies, earlier version was actually correct. Satisfies uh, xp minus 1 over q, and xip cannot satisfy xn minus q for any n less than p, right? This is because xip is the primitive root. root of unity. So as is it is the primitive root of unity. So in the roots of unity forms as we already discussed it, they forms a multiplicative group, and JP has to be the generator of that multiplicative group. So its order has to be the same as the order of the group, which is P. So it cannot satisfy a polynomial of a polynomial of this kind which has degree less than P, right? Because it's a primitive root of unity. So now this satisfies xp plus 1 and also so let us say fx is this xp minus 1. Now what is xp minus 1? This is not, you can write it as x minus 1 1 plus x square dot 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 x raised to p minus 1. So we also know so we know that f of this JP is 0 because it satisfies this. This implies JP minus 1 and 1 plus JP plus JP square dot dot JP P minus 1. This is actually 0. So as we are in rational, so either this thing is 0, this is equal to 0, or this is equal to 0. So can this be 0? No, right?
Yes, primitive pth root cannot be 1.
Yeah, so primitive root cannot be, since JP cannot be equal to 1. This is primitive root. Therefore, it must satisfy the other polynomial. Therefore, 1 plus JP plus JP P minus 1, that is equal to 0. So somewhere I am using this, or somewhere I am using that notation. So let me just be constant. So what does this mean? That it satisfies the polynomial? This implies g of JP is equal to 0, where gx is 1 plus x square dot 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 x raised to p minus 1. So it's a degree p minus 1 polynomial, and JP satisfies this. For with that, you can say the degree of JP over Q is less than equal to p minus 1. But we want to show that it is precisely p minus 1. So we should show that the above polynomial is irreducible. But how to show that? So for that, first observe, I should write what I am saying. So now we should show that gx is irreducible. And how to do that? For that, first observe that gx is irreducible if and only if gx plus a is irreducible for all a in where a is any integer. Oh, sorry, integer or rational, I think. We actually need just one is reducible where a belongs to q. And how to see that? So this is not difficult. So if gx is say reducible, gx is equal to hx kx, then gx plus 1 will be nothing but hx plus 1 kx plus 1. So gx is reducible. What does this line means? This means gx is reducible implies gx plus 1 is reducible. And similarly, if gx plus 1 is say some hx kx, then you just replace x by x minus 1, you will get that. Oh, I should show it for any a. So this is a, this is a, this is also a, this is for a, this will be minus a minus a. So this is gx plus a is reducible, implies gx is reducible. So it's equivalent to prove check the reducibility for some gx plus a. Okay, so now for gx is equal to 1 plus x dot 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 plus xp minus 1. This is the same, we saw that this is x nothing but xp minus 1 divided by x minus 1, because xp minus 1 has a factor x minus 1. Now what is gx plus 1? Gx plus 1 is nothing but x plus 1 raised to, let me write it in some other page. Oh. So let me write it in the next page. So what is gx plus 1? Gx plus 1 is nothing but you just replace x plus x by x plus 1. This is x plus 1 raised to p minus 1, and this will be x plus 1 minus 1. This is x. Now you apply your binomial expansion. It will be xp pc1 xp minus 1 dot dot dot. You have p raised to x plus 1 minus 1. This will be cancelled, and then you have x in the denominator. So gx plus 1 will be nothing but x raised to p plus pc1 xp minus 1 plus pc2 xp minus 2 plus dot dot dot. You have px here, so, and p does not divides 1, which is the coefficient of this, but p divides pc1, p divides pc2 dot dot dot. P will divide pcn minus 2, and p will divide pcn minus 1, which is p, and also P square does not divides P. So by Eisenstein criteria, G of x plus 1 is irreducible over Q. Which implies Gx is irreducible over Q. And thus you have the degree of QCP over Q to be just P minus 1. Okay, so this itself is a important result, as I already told. So just keep this keep this with you. So now all the options should be very trivial. There is nothing much to do. So yes, so let's start with the first option. If P less than equal to Q, then CP belongs to Q of CQ. So as you already said that if you take P to be 5, Q to be 7. So for first, take P to be 5, Q to be 7. Then how can you reach to the contradiction? So you want whether CP will be there inside QCQ. So if psi 5 belongs to psi Q of psi 7, then we have the tower of fields. You have Q at the bottom, then Q psi 5, and then you have Q psi 7. What is the degree extension of degree of this? This is 6, and the degree of this is 5 minus 1, which is 4. So this will implies 4 divides 6, which is a contradiction. You get it, Muthu? It's okay. So this is false. Now, what about the second one? It says P divides Q minus 1, then psi P must be there inside Q psi Q. So for that, you just take P and Q such that P divides Q minus 1, and the same contradiction you will get. So for that, consider these two primes. Consider P to be 11, Q to be 23, then 11 divides 23 minus 1, which is 22, but what is the CP belongs to Q of CQ. But if CP belongs to Q of CQ, oh, this should be belongs to, then by the above tower of fields, by the following, let me just write, by the following tower of fields. So what is the tower of field we have? Here we have Q of 23. Here we have Q of 11, and here we have Q. Its extension is this has degree 10, this has degree 22. This is just 11 minus 1 is equal to 10, 23 is equal to, this implies 10 must divides 22, which is a contradiction. So this is also false. Now the third one, which says Cp belongs to this, then P minus 1 divides Q minus 1. So that's already done in part first and third. So this is true by the ideas used in first and second.
The towers per second problem, sir. Q to Q23 or
Yes, yes. Thank you. Thank you. This is 23 minus 1. I hope I haven't done this silly mistake above. Yes, here it is. Okay. Good. Thank you, Mithu. So the fourth one is, if there are just a field homomorphism from phi Cp to QCp to QCQ, then P minus 1 divides Q minus 1. So this need a little bit of argument. So let me just quickly prove this. This is true. So let sigma be a field homomorphism from sigma from Q of Cp to Q of CQ. So then by the results, or I can just simply write, then since psi p satisfies xp minus 1, then what can you say about sigma of psi p? Yes. Sorry. So see, then since psi p satisfied xp minus 1, therefore sigma of psi p must also satisfy, so satisfy xp minus 1. This implies sigma of psi p, this is some psi, this is some zeta kind of notation, zeta is a pth root of unity. Now observe that sigma is injective. Why this is so? Because for all alpha belongs to Q, you have mm, sigma of alpha is equal to alpha, and we are interested in uh, sending this to a non-trivial root, of course, or I think we can argue this in a better way. Yes. So this is a field homomorphism, right? So definitely this will imply the kernel of this sigma is not trivial. This is not just zero. So the only ideals of a field are just zero ideal and the entire field. So kernel is not the entire field, right? Q of JP. So this will implies the kernel has to be zero, right? Or in fact, uh, you can argue like that since this is a field homomorphism, so one belongs to Q, so sigma of one has to be one, not sigma of one is just one. So kernel of sigma cannot be the entire psi p. You have already one element, so kernel of sigma has to be zero. Okay, because you have only two choices for the kernel. So this sigma is injective. That means this implies that sigma of JP is also a primitive root, because the injective map will send the primitive root to primitive roots. Uh, Now, what can you say? So, is also a primitive pth root, pth root. So, now sigma, where this sigma of Zyp lies, this is inside uh, the domain, the codomain thing, right? Sigma of Zy, this is Q of Zy, Zyq, right? This sigma of uh, Zyp lies in Q of Zyq. So you consider the tower of fields, the same tower of fields. I have drawn this tower a number of times. So like Q sigma of Zyp, and then you have Q of Zyq here. So this lies inside this. So this has p minus 1 degree because now it's a primitive root. This has q minus 1 degree. This is due to primitive root. That's why we need to show that this is a primitive root. Okay, and this will implies that p minus 1 divides q minus 1. So hence the statement is true. Is it clear?
Clear.
Okay. So let's quickly finish the last question also. I was prepared with assignment 6 also, but I don't have time. So maybe in the next lecture, I will solve first the 8th assignment, and if you have any doubt in the 6th one, then you can also ask. Okay.
So we are meeting next week also.
Yes, from my side, definitely yes.
Okay, then we will stop here. Now it is already.
What you are saying?
So the sixth problem we can continue from the starting of the next class.
I will just say some hint because I want to start uh, assignment 8, or you want me to finish it in the next?
Yes, yes.
Okay. So if that is the case, then it's okay for me also. Okay, then we will stop here and we will meet on next Friday. We will first solve this 6 problem and then assignment date.
Yes.
Okay. Thank you.
Thank you. Thank you.
Thank you. Thank you, Muthu. So you are coming next week also, right?
Yes, I will come.
Okay.